All right, our next speaker this morning is Lizzy Teryoshin, who's joined us from UC San Diego. Lizzy's been working this summer with David and will tell us about their project together, a study of supernova breakout simulations, ejecta morphology and dynamics.
Thanks, Gwen, for the introduction. I've had a great time working with David so far this summer, and I'm really excited to tell you all about what we've been working on. So, why should we care about supernova? Well, we know that supernova are the primary drivers of galactic chemical evolution and affect things like star formation rates and stellar winds. Supernova are also the source of elements that make up life. Hence, having a solid understanding of supernova physics is a prerequisite to understanding almost anything else that we might care about in astronomy. We know that neutrinos are the main drivers of core collapse supernova, but in spite of their significance, uncertainties remain regarding their precise role in the early seconds of the explosion and the subsequent impact on ejecta morphologies. Perhaps the biggest issue in previous work done on supernova is that simulations have suffered from computational limitations. This has meant that people relied on 1 or 2 dimensional simulations or simulations which used coarse approximations of computationally expensive but still important things, namely neutrino physics. Previous simulations also did not live up to what we expected from observed core collapse supernova like Cassiopeia A, which is shown in the picture on the right and is one of the most studied core collapse supernova remnants in history. Luckily for us, improvements in high performance computing have made running high fidelity 3-dimensional core collapse supernova simulations feasible. And this summer, I'm running one such simulation using a 3D hydrodynamic code called Flash. My goal will be to describe and quantify asymmetries in both the shock and in the distributions of ejecta. So what makes our simulations special? We inherit a 25 solar mass, solar metallicity progenitor evolved in a 1-dimensional hydrodynamic code called Kepler. At the onset of core collapse, the core of the star was mapped to Fornax, a 3-dimensional radiation hydrodynamic code where the core was evolved until neutrino heating subsided, around a few seconds. This is where we differ from previous work. Fornax considers detailed neutrino heating and transport in 3 dimensions, which we know is significant for at least a few seconds. Nevertheless, previous simulations only considered neutrino heating for timescales on the order of less than 1 second. We consider neutrino heating for 5 to 6 seconds. We don't know how the increased accuracy and duration of neutrino heating will affect the final distribution of ejecta and the shock breakout, which is partly the question that we hope to answer. My role was to continue to evolve the supernova out to shock breakout and flash. Later on, we can send our data to collaborators who can then reconstruct light curves that we would have observed from this supernova and then compare it to observations. So on to some of our results. Shortly after mapping from Fornax to Flash, we see obvious asymmetries in both the shock and in the distribution of nickel 56. The left plot shows entropy through an equatorial slice of the star, and discontinuities in entropy tend to be a good visual indicator of where the shock is. The right plot shows the mass fraction of nickel 56 at the same time, around 40 seconds into the simulation. Nickel 56 is significant because it tends to correlate with other iron group elements, and its radioactive decay powers the light curve that we observed from supernovae. The shock is the discontinuity in entropy around 400,000 kilometers from the center of the star. At this moment, the shock is moving with a velocity of around 8,000 kilometers per second. At this moment, we also observe bulk nickel 56 velocities on the order of 3,000 to 4,000 kilometers per second, which is comparable to the velocities of iron-rich ejecta that we observed in Cassiopeia A. At this time, we also see 2 large plumes of nickel, one extending to the northeast and another to the southwest. This largely mirrors asymmetries that we see in the shock, which also extends further to the northeast and southwest. Something that you can't quite get from the plots is that at this moment, most around 80% of the nickel is located in the southern hemisphere of the star. This largely mirrors the asymmetries that we see at later times. These plots show the mass fraction of nickel 56 through the equator of the star and through a vertical slice of the star around 2 days into the simulation. The green line is the hydrogen-helium interface, which I've defined as where the mass fraction of hydrogen is equal to the mass fraction of helium. We can see that early asymmetries have survived. We see the same plumes extending to the northeast and southwest, and most of the nickel 56 has remained at the bottom of the star. This indicates that asymmetries, which were likely influenced by neutrino heating in the early seconds of the explosion, can survive out to late times and impact the final distribution of ejecta. Hence, the physics governing the early explosion has the power to significantly impact the final distributions of ejecta. Something else intriguing that we see at this time is a reverse shock, which is evidenced by yet another discontinuity in entropy further in towards the center of the star than the primary shock. We don't know how this might affect the distribution of nickel 56 as the simulation progresses, or whether the plumes will survive the reverse shock. Here, the nickel 56 plumes flatten as they run into the hydrogen-helium interface, and further interaction with the interface, as well as with the reverse shock, might break apart the plumes into some surviving bullets, which are bits of nickel being flung out at high velocities. Here you can see a bit better what I mean by bullets. As the nickel runs into the hydrogen-helium interface, it splits apart into these fingers and pushes the interface further southwards. This indicates that, to an extent, the nickel 56 plumes define the shape of the hydrogen-helium interface, as opposed to just filling in existing gaps in the interface. This is also the first place that the shock breaks out from the center of the star, as you can see as that the discontinuity in entropy reaches the surface of the star in the bottom of the plot on the right. So some more on the velocities of nickel 56. We observed a correlation between radius, radial velocity, and mass fraction of nickel 56. The plot on the left is an isosurface of nickel 56 at a mass fraction of 3%, only showing those regions with a radial velocity above 5,000 kilometers per second. The isosurface is colored according to radial velocity, with darker red corresponding to higher outwards radial velocity. The plot on the right shows an isosurface at a mass fraction of 25%, once again only showing those regions at a mass with a radial velocity above 5,000 kilometers per second. From the plot, we can see a correlation between radius and radial velocity, as nickel further from the center of the star tends to be moving faster. We also see a correlation between mass fraction and radial velocity. Visually, there's quite good agreement between high velocity, high mass fraction cells and high velocity cells in general. And indeed, most of the nickel moving at high radial velocities is located in high mass fraction cells, and around 1/3 of the nickel in high mass fraction cells is moving at a high velocity, as opposed to just 1/5 of the nickel overall. Here, the nickel 56 velocities range up to 10,000 kilometers per second and have an average velocity of around 3,500 kilometers per second. The nickel 56 slows down considerably upon reaching the hydrogen-helium interface. The left shows the mass fraction of nickel 56 through the equator of the star around 2 days into the simulation, and the plot on the right is an isosurface of nickel 56 at a mass fraction of 3% at the same time, once again colored according to radial velocity. From the plot on the left, we see that the nickel 56 plumes do not cross the hydrogen-helium interface, and hence they slow down to match its speed. From the plot on the right, we can see that the maximum velocity of nickel 56 is around 5,000 kilometers per second, whereas before it was closer to 10,000 kilometers per second. The average velocity of nickel 56 has also decreased from 3,500 kilometers per second to just 2,700 kilometers per second. To wrap up, we found that our simulation was able to self-consistently reproduce observed properties of core collapse supernova like Cassiopeia A, including explosion energies, ejecta velocities, and yields. Although comparisons to observed core collapse supernova are still early, our results provide evidence that neutrino heating, aside from being the dominant driver of core collapse supernova, when evolved in 3 dimensions, can reproduce observed diagnostics. Had we not considered neutrino heating for so long, we would have seen smaller explosion energies, smaller velocities, and less pronounced asymmetries. The initial asymmetries influenced by 3D neutrino heating can survive out to shock breakout. Our results provide initial conditions for calculating light curves resulting from the supernova, which we've been able to reproduce with stunning accuracy for other models. And aside from continuing to evolve our supernova out to months and days, the next step would be to run a wider variety of core collapse supernova simulation with different masses, explosion energies, and envelope profiles. One last limitation is that although the inner core of our star was evolved in three dimensions, the outer envelope was mapped from Kepler, a one-dimensional code. It would be interesting to see what effects a convective 3D envelope would have on the outcome of our simulation, which is something that we intend to explore in the future. Thank you all for your attention, and I'll take any questions people have.
Great, thank you, Lizzy. Any questions? Tony?
What the time difference was breakout at one radius and one direction versus the other direction?
It's sort of, I wouldn't know the exact, like, when the latest time was that it reached the surface. The first time it happened was at around 2 days, and then I think the latest it might have broke out, I think, was closer to like 3.5 days. So there was quite a big discrepancy between like where the shock hit first and where it hit last. So like towards the top of the star, it was like closer to like 3-4 days.
So light at those stochastic PAH showed that it was probably a course so far. So it might be interesting for further comparisons to actually include how this is.
Yeah, that is something that we intend to look at, sort of like interactions between, like, looking at core collapse supernova and stripped stars, is something that we also intend to look at in the future.
Other questions for Lizzy?
Well, good question from Andy. I'm curious whether your new calculations significantly affect the amount of fallback onto remnant or remnant mass compared to other calculations.
I wouldn't know how much, what other calculations saw for their remnant mass. At least in this model, we saw quite a lot of fallback, like on the order of 3 solar masses, which my understanding is quite a lot compared to other simulations, but that's not something that we've like paid a ton of close attention to.
Right, very nice. Let's thank Lizzy again.